Hello, my name is Su-Wei Qi. I am an assistant project manager from Datong Forever Energy. You can call me Michael. My topic today is Introduction to Solar Photovoltaic System Engineering. First of all, I will talk a bit about what is solar photovoltaic system. Before designing the system, we need to do some site survey. After the survey, we need to choose our equipment. And in the end, we will come up with a system design layout, which will serve as the cornerstone of the whole project. The PV system is composed of photovoltaic modules, also with inverters, and some other electronic components. Now, if we look at this picture, you can see that the modules are placed on the roof to receive the sunlight. The modules usually generate DC current, but the electricity we use in our daily lives are mostly AC current. So we need to have a component called the inverter to convert the DC current to AC current. And in the end, we will inject the electricity into the power grid of the power company. The PV system refers to this whole process, and this is a diagram that represents the typical PV system. The balance of the system mostly includes the construction, which is the foundation, and the inverter. These two are the major components of the system, and also the solar module. Next, we have the DC switchboard, the AC switchboard, and in the DC switchboard, there will be components such as the isolating switch, the sub-absorbers, and the fuse. They are mainly used for protection. In the AC switchboard, there will be a breaker, which is NFB, and an electricity meter. The meter is used when we want to inject power to the power company's grid. It can calculate how much electricity was injected, and thus we can sell the electricity to the power company. Now, besides the components that are mentioned above, there are also the conduits, wires, and cables. Together, they are the main components of a PV system. So in this picture, you can see the PV array, the junction box, it could be DC or AC, then to the inverter and the AC box. The AC box is mainly used for consolidating and has a protective switch inside. The last part is when the electricity is injected into the grid. There are several types of site survey depending on the site. There are sites that are on the ground and on the roof. The ones on the roof can be divided into RC flat roofs, or like the one my cruiser is pointing at right now, the diagonal or tilted roofs. For the RC roofs, we will evaluate how high should the bottom point be, what should the angle be for the tilt, in order to design a system with a better productivity. And of course, this would also depend on the size of the area. How big of an area do I need to achieve my expected energy production? So for the diagonal rooftops, I will inspect the material that the roof uses and try to come up with a material that can be best secure the system on that roof. Also, how tilted is the roof? The condition of the roof panels. Are there any leaks or is it rusty? If the condition is bad, we might do some renovation or we might even consider giving up on such a case. Now, for the sites on the ground, we will see how spacious the area is, or if it's used in the parking lot, or it may even be over a water pond. We will evaluate them all. Take the parking lot, for example, we would need to know how big each of the parking spaces are, what are the parking demands and the car's route in the parking lot, because we need to plan everything in advance. Also, what types of cars will be parked here? Are they big or small vehicles? For the typical sites that are on the ground, it's a bit simpler, but we would need to know the geology of that site. Was it a landfill before? If it is, then that means I can't secure my structure's foundation by drilling it down. I would need to use these large blocks in the picture to secure the foundation. Now, for the ones that are over the water, we need to consider the hydrology. For example, the flooding situation over the past 20 or 50 years. If there are any ongoing flood control operations in the area, will there be a flood? These are the things that we need to evaluate when surveying the site. Once we arrive on the site, we will measure the parameters of the site. We will measure the length, the width, and check if there are any shades or potential shades from the surrounding buildings and obstacles. Looking at the picture in the upper right hand corner, since there is an extension of the roof, so at that period of time, it will project a shadow in the area. And we would want to avoid this. So I would avoid putting the systems, the modules, in the area that is covered by the shadows to prevent the shadow from interfering with the insulation and the productivity of the system. For the tilted roofs, we will also go onto the roof to take measurements to check the conditions of the roof boards. And if you see in the picture in the lower right hand corner, the tall roofs on the roof are called 太子楼. You can see that these tall ridges create such large shadows at that time of the day. So I would take all of these into consideration when designing the system. After surveying the rooftops, I will walk around and check the electricity contact points nearby. Generally in Taiwan, the main business model is to inject the electricity to the power company's grid. So I will check the power company's local equipments nearby. If we look at this power pole, I will check if there are other power poles nearby that can be used as liability points. Also, the voltage transformer. I will also try to negotiate with the power company to see if it is possible to lay an additional cable to connect to our system. In the end, when our system is fully installed and the power meter is in place, I will connect the cables to our switch box, which is what we call a liability point. A liability point is a point where starting from that point on, anything that goes towards the system, it'll be the vendor's responsibility. Anything that's going to the power grid, it will be the power company's responsibility. So it's a point to divide the area to make sure that both sides are clear about where their liabilities rest. Now, when we're choosing the equipment, we can look at it from the modules aspect. It can be divided into upstream, midstream, and downstream. Upstream is mostly materials such as the silicon wafer. Silicon can then be divided into polycrystalline silicon and monocrystalline silicon. In the past, it's mostly polysilicon, but in recent days, we use monosilicon because of its performance. Its performance is better. That's why the solar cells that are used mostly are composed of monocrystalline silicon. No matter if it's mono or polysilicon, we will build them into silicon ingots. It's kind of like compressing them into a brick. They are all made from silicon materials. Then we will slice them into wafers. Now, the difference between mono and polysilicon is that polysilicon can be made into a complete square, but not monosilicon. So if you look at the picture, you can see that the four corners of the monosilicon are actually a bit of a curve. So you can easily determine if your module is using a monosilicon solar cell or a polysilicon solar cell by looking at the panels. Now, once the silicon is sliced into wafers, they will then be sent to the midstream. Vendors of the midstream include battery makers and module builders. They will perform arc welding on the wafers to create the circuits on the solar cells, and the last step is to send them to the downstream module vendors for packaging. Then system integrators like us will purchase these components. We will go and compare the cost and the performance of different modules from different vendors to determine which brand should we use and how big should the capacity be for the site that we are working on. As mentioned previously, besides the monosilicon and polysilicon, which are silicon materials, there are also non-silicon materials for the solar cells, such as the amorphous silicon solar cells. In the past, there was even the gallium arsenide indium phosphide semiconductor and the CDS or CDTE semiconductor, and also some nano level ones too. However, the most popular ones that are used nowadays are the monocrystalline types. They are still the majority. The reason is their conversion efficiency is way better than the other ones. The cost, the cost for the monocrystalline ones are also cheaper than the others. So take the gallium arsenide indium falsified semiconductor for example, though it has a good conversion efficiency, but the cost is too high. So when we take the cost and performance into consideration, we will choose the solar cells that are made from silicon to be our component in the system. The solar cell has multiple layers. From top to bottom, it is glass, PV glass, in particular to prevent any reflection. The reflection rate needs to be so low that the cells inside get absorbed as much insulation as possible. Next would be the EVA films. Its function is to prevent water vapor from getting into the battery cells, which could affect the efficiency of the battery. And lastly, the whole panel will undergo waterproof procedures. So the solar battery electricity mechanism is when the N-type silicon and P-type silicon in the cell absorbs light, it will generate the positive and negative of a battery. There will be two circuits coming from both of the positive and the negative side, and they will converge into the junction box. Then there will only be one positive and one negative wire coming out of the junction box. And basically, there you go, a solar battery. Now, only DC has a positive and negative. We have mentioned the modules part. Next, we will talk about the inverter, which is the component that converts DC to AC. There are different types of concepts on inverters. There is the central inverter, which is an inverter that receives all the power coming from the cells. Now, the most common one used in the field is the one in the lower left corner, which is the array or string inverter here. Its benefit is that it is very flexible. When we are on site, there might be different kinds of roofs. I can use different inverters with different modules to deal with these different types of roofs. It allows the power generation to be evenly distributed among the inverters. So compared to the central inverter, assume your site is an open site and faces all directions. The central inverter would focus on the south side, but it will be affected by the ones that are facing, say for example, the east side. That's why there is the array or the string inverter to help complement these kinds of conditions. So if we consider it from an operational perspective, most people would prefer the array or string inverter because the limitation of a central inverter is that if something goes wrong and you need to shut down the inverter, you'll actually shut down the whole site. But if you're using the array or string inverter, you'll only need to shut down the inverters that are having problem. You won't affect the whole system. So over here is something that we call a module inverter concept. It doesn't control a whole array or string, it controls a piece of module. It's the concept of having one inverter per module, yet relatively speaking, the total cost would become higher, but the power generation rate would be higher compared to the others. Since the inverter is installed on each module itself, the only drawback is the total cost would become higher. Now let's take a look at this graph. If we pay attention to the yellow curve, if today the installed capacity is 25.6 kilowatts and the users want to make use of the short period of time around sunrise and sunset, they would need to raise the installed capacity of the inverters. And that is to add more modules to raise it to maybe 30 kilowatts or even 35 kilowatts. This is something we can design and implement within the limitations of the inverters. So the gray area you see here with the stripes, it basically represents the additional amount of electricity generated. If my installed capacity is only 25 kilowatts, then my energy production would be here. If I increase my installed capacity, then I can generate this amount of energy production. Now, combining the modules and inverters along with some design and measurement, we can propose a layout like this. It would have the measurement of the site, the coverage of shades in the area, the obstacles in and around the site, and after drawing them, we can start to lay our modules on the layout and divide the modules into different zones, and then decide which inverter should this zone go to, which inverter should that zone go to. Then string them all together in the end. After this, I will think about the stands and the racks. How high should the bottom point be? How high should the top point be? What is the tilted angle? I will use this information when drawing the layout of the design. Now, as you can see in this picture, it is an aerial view of the site, looking at the site from the sky. The bottom of this layout is south. This layout was designed with the bottom facing south, so you can see that the estimates of this site is actually really good as it is facing south directly. After designing the layout, we will begin to draw the single line diagram. There is the AC single line diagram and DC single line diagram. The AC single line diagram will include the switch box that we mentioned along with the electricity meter, which is the one my cruiser is pointing at right now. Also the liability point. It might be written on the copper plaque here or on the power pole outside, depending on how you negotiate with the power company. Now after drawing the AC single line diagram, I would also put down the number of corresponding inverters, their capacities, and the kind of cables that are being used. Also their diameter and measurements, and also where the switch is. I will put them all down in the chart. After talking about the AC part, here is the DC single line diagram. From the module to the DC switchboard, there will be DC switches, surge absorbers, and fuses. We will negotiate all the components in the diagram with the power company, and we will also send the diagram to the power company to have it reviewed. Once they've cleared it, we will start to design the engineering part of the project. Now, this slide basically covers the things from site survey all the way to producing the layout of the site. And in the next part, I will talk about the design of the structure along with engineering and construction of some cases that we did. As mentioned previously, there are different kinds of sites. There are ones on roofs, on the ground, and also on the water. The ones on the ground are usually used in places where there is abundant space, where it's very spacious. For sites on the ground, we can use the screw pile method to pile, but before that, we will check the geology of the site. And after knowing the geology, we can determine how deep should we pile and what materials should we use to pile. After that, we will double check if the parameters are as expected before we move on to designing the stands and also the racks on the tops. And this is the part of piling. Now, besides piling, we can also use big blocks of concrete to lay the foundation. We can use this method when we can't pile. Maybe the ground used to be a landfill and the structure is not stable enough to withstand the piling, or the piling may accidentally penetrate the protection layer below. It will contaminate the surrounding environment. So in these cases, we will choose to use these big concrete blocks instead. The way to make these blocks is to create the molds first, then pour the cement and aggregate mixture into the mold. Once it's dried with the shape we like, we take away the mold and install the steel structure of stands and racks onto it. Then we will start to lay the modules onto the steel rack, and there you go, the preliminary foundation of a site is done. After talking about sites on the ground, next we will talk about sites on the roof. There are different types of roofs. There's the RC flat roof, where we can use scaffolding. Actually, we can also use the big blocks of concrete we mentioned on the roof, because some buildings won't let you drill on their rooftops, so we will make some adjustments. As mentioned previously, when performing foundation constructions on the roof, I will use the data and design provided by the structural professionals to plan the construction details. So if we look at this roof, take this flat roof for example, I will first plant rebars, drill and plant the bars, then clean up the dust and dirt. Then I will put on the bolts and inject the adhesive. The adhesive is the red thing you see in this picture. Its purpose is to prevent water vapor from getting in, and also strengthens the firmness of the rebar and the roof to kind of combine it with the whole structure. After the foundation construction is completed, I will move on to setting the posts and racks for the steel structures. After it's done, it will look like this picture on the upper right hand corner, where we will make some adjustments. Next, we will lay the solar panels onto the steel racks, and in the end, we will make the concrete bases of the stands. Its purpose is to have better waterproof properties to prevent water vapor from getting into the roof structure. These pictures are using the same method, yet from this picture you can see that the base and the stand's height is a bit different from the picture in the previous page. The previous stand's height is around 3.5 meters and this stand is around 1.8 or 1.9 meters. Basically, we determine the height of the stand according to the conditions on the site and our discussion with our customer. Of course, when you are determining the height, you need to consider if it's convenient for future maintenance and operations. If it is too low, then it's actually pretty inconvenient for the maintenance crew. As mentioned previously, we can also use the big concrete blocks on the rooftop. When you take off the modes on the roof, it will look like the pictures on this page. For diagonal roofs, there are multiple ways to do it. As mentioned in the previous site survey part, you need to check what type of diagonal roof are we dealing with. Here you can see that for these kinds of roof panels, you can use these kind of saddle-like foot to secure your racks. So there are different kinds of feet you can choose. Then we will put on waterproof tape, and after securing the feet, we will use something called the silicone to cover the feet to prevent water from getting in. And the lower left picture is when we install all the aluminum racks onto the feet, then we lay on the solar panels in the end. The previous page is when we need to drill into the roof panel. But for these diagonal roofs, we can't drill into them. So we will use these kinds of clamps and also apply waterproof tape. The waterproof tape is the black thing you see here along with the clamp. Then we install the aluminum racks and lay down the solar panels. There are two ways to secure the modules. There is the 6 anchor point method and the 4 anchor points method. The difference between the two is that, as you can see in the left picture, there are 1, 2, 3, 4, 5, 6 points. And for the 4 points, there will only be 4 points. So basically, we will determine whether to use the 6 points or 4 points based on the wind speed at the site. Looking at these pictures, if we are dealing with a flat roof, we usually anchor 8 points. We will have 4 points on the top and 4 points on the bottom, along with the L feet to make the whole structure of the system stronger and more secure. Actually, in recent years, the more popular ones are the ones on the water, because first of all, it is faster to build, and actually the cost is also lower when compared to the ones on the ground and on the roof, because most of the material it uses are made from plastic. Now, the way to build the site is first you will need to build a platform that is going to be placed on the water. Once the platform is made, assemble the parts on the platform and install the modules. When everything is installed, push the whole platform with the system on it into the water. Then make some necessary adjustments in the water. A drawback of this kind of site is that you can't control where it faces, unlike the ones on the roof where you can set it to face a fixed direction. You will need to push the whole system and platform into the water first, and then adjust it from there to get the awesomeness you want. The core technique for these kind of sites on the water is the anchoring part. We will do a site survey to evaluate which kind of anchoring technique best suits the site. There are a couple of techniques such as bank anchoring, like what this top left picture is showing. They will put the anchor on the bank to make sure that the platform stays in place. If a site can't use bank anchoring, then we might use big blocks of concrete as the anchor and put them into the water to serve as the anchors. Besides using the concretes, there is another way, and that is to suck out all the water first and then drive a rivet into the ground in the pond or in that body of water to serve as the anchor. Now let's take a look at the construction to connect our site to the power company's power grid. First, we will discuss with the power company on how to connect both ends. The power company will tell you the position you need to extend your pipelines to. Then they will work on the connecting part. So basically, this construction can be separated into the construction of the cables and pipelines, and the construction on the electronic equipments. For the pipeline and cables construction, the users will usually have the pipelines installed at the designated place in advance. Then the power company will send their engineers and workers to complete the rest of the connection construction. So this is the part about connecting the system to the grid. Following up on the different kinds of sites that we've talked about, including the ones on the roof, the ones on the ground, and the ones on the water. Now, because the ones on the water are newer, well, not actually newer, but are more popular in recent years, so I used red characters here to highlight them. Now from this table, we can compare the difference between installing the system on water, ground, or roof. The biggest difference is actually the energy production efficiency. Yeah, so energy production efficiency, because sites on water have water to help with the ventilation and cooling, their heat dissipation is better. So having the system on water can also help in preventing the water from vaporizing from the surface, and can also help surpass the eutrophication, because the system will block the sunlight from reaching the surface of the water. Now, in the latter parts, I will talk about some situations where the structure is more vulnerable to be damaged. So at our company sites, we will pay attention to these details during the construction. If we look at foreign sites or even the sites in Taiwan, damages are often caused by storms and strong wind. So taking Taiwan for example, we often have typhoons. In the past, because people had limited experience, so they didn't pay much attention to the details when building the structures. Like, first of all, the size of the model might be different from the size of the rack. And second, it may not be designed according to the wind force. So when a typhoon hits, the instant wind force is too strong that it blows the module away. And also, there weren't any lateral support bracing. And then usually there was only weights on top, and maybe the weights weren't enough. So other details include the lack of shock resistance upon earthquakes, and the module's design was too fragile to endure the environment. Now, how do we adjust it to make it better? The first is, besides the weights on top, add additional locks to secure it from below, like the 8 points we mentioned previously. Also add lateral bracings to make it stronger, because in the past, some sites will look like this. This is a piece of module, and they only secured 2 sides of that module. So yeah, just 2 sides. Now for sites nowadays, we might add an extra bar or rack in the middle to give it more support, to make it stronger and to make sure that it doesn't get blown away easily by strong winds. And third is to add fortifying components, such as adding the L feet on the frame of the module to enhance its ability to withstand strong winds. Here are some pictures of damagement from sites that are overseas. We will take these cases as reference and prevent this from happening to our sites. Now, the overseas sites structures are different than the sites in Taiwan. So, for example, if you take a look at the picture that my cruiser is on right now, you can see that its foundation is actually built on these small pieces of concrete. So, if the wind is too strong, these concrete little blocks will not be enough to hold your whole system in place. And the result will be as you see in this picture where the whole system collapsed. The previous slide was talking about the structure. This slide is talking about the damage of electronic equipment. There are a couple of types of damage as listed in the table below. Sometimes the glass of the module gets damaged, like what is shown in the previous page. Sometimes when the wind is too strong, it will lift the solar cell from below. Also, there is the damage on the aluminum frame. Now, in the previous slides, we've mentioned how to prevent this from happening, and that is to add L feet on the inner side of the frame to strengthen its ability to withstand strong winds. As for electronic equipment, if you didn't secure your cables and wires, as the wind blows, it will swing and the wires and cables will swing back and forth, and that it is likely that these connectors will become loose and may even break the wires and cables, which is very dangerous. As mentioned previously, there's the 4 and 6 anchor point method for diagonal roofs. Now, usually in foreign countries, they would use the 6-point method since their module is bigger. Take this guy in the picture for reference. Let's assume he is 1.7 meters tall. This module he is laying on will be approximately the same length. So we will add an additional anchor point in the middle, making it a 6 anchor point in total. Coming back to our sites, in the past we use aluminum racks on roofs. However, since aluminum racks cannot withstand strong winds, if you really want to have it withstand strong winds, you will need to change the entire structure of the system. So now we've changed our materials for making the foundation of the steel structure to hot dip galvanization HDG, or the magnesium aluminum zinc coating, with the height of the stands depending on the use and conditions of the site. As I mentioned, for diagonal roofs, we use these anchors to help secure the modules. Now, looking at the diagram below, you can see that a single module has 3 aluminum racks supporting it with 6 anchor points. Here are the various types of anchors to secure the racks. There's the ones that directly penetrate the roof panels or the ones for RC roofs. Though it's a RC roof, the one we're talking about here are the diagonal ones. They have tiles on top of it, so we'll take off the tiles and plant rebars. Also, you'll see those roofs that uses clamps. Now, looking at our sites, before the whole construction process, we will ask the vendors to provide the inspection documents on the materials that will be used. Also, the structural engineer will need to endorse the designs, then we will begin the whole construction process. Now, since there are a lot of typhoons in Taiwan each year from experience, so we will further strengthen the structure after it is installed. So, for example, we will apply the silicone or thread locker on the bolts to prevent the screws from loosening. And also, we will trace the outline of the bolt. So once we have the lines traced, then the maintenance crew can tell if the bolt is loosened on their periodic checks. And we will also add these Teflon gaskets, which is the thing you see in the picture. It is white. Their purpose is to prevent the aluminum frame from touching the steel structure, in which case may cause an electric potential difference. Regarding to the enhancement of the electrical parts, we will tie all our cables to the racks and stands so that when encountering strong winds, they won't be stretched or loosened or even break in half like what we have talked about in other cases. Now, as you see in this picture, we will also use silicone to fill in the gaps between the wires to prevent bugs or small animals from crawling into it and eating the outer coating of the wires, which could be very dangerous. The latter part is basically some materials that I've prepared regarding to the sites on the water. For these kinds of systems, as I mentioned before, their power generation and ventilation conditions are better than the ones on the roof and the ones on the ground. These are the advantages and features for the sites on the water. It is for your reference. This chart was also mentioned in our previous sessions, and that is for the systems built on the water, their power generation is indeed greater than that of the flat or diagonal roofs, and it is higher than the two by nearly 5%. I've also mentioned before that the most important thing for these kind of sites is the way they anchor the sites, which is the core technique in these sites. This is a comparison table between Taiwanese floating platform vendors and other market-leading vendors from different countries. It is also for reference. There is France, Taiwan, Japan, Korea, and also China. The slides in the back are basically introducing the materials that each vendor on the chart uses. We will just quickly go over them as they are for your reference. Now, this page is a French vendor. They also use HDPE as their material with aluminum alloy. Their installation steps are basically the same, where you form the platform on dry land first and then push it into the water and anchor it when it's done. Now, allow me to quickly skip to the part in the back, which is talking about the core technique, and that is how the anchoring is done. These pictures show what the sites look like once they're done, again for your reference. Now, this is a site in Taiwan. You can see that it also uses HDPE, but instead of the aluminum alloy, they use the super dyma steel as its structure. Now, if you use the method shown on this Taiwanese site, you won't be able to assemble your platform on site and push it into the water. You will need to assemble it first in your factory and then use a crane to help lower it into the water once it's done. It will take more time this way. Here are the installation steps. Now, for the sites in Japan, what's different than the other countries is that besides using the HDPE, they will fill the inside of the structure, which is the one you see now, with styrofoam to enhance its buoyancy. And they also use the aluminum alloy as the frame. These are the installation steps. In this picture, you can see that the sites on the waters are usually formed from big floating platforms, so its installation speed is actually pretty fast. Now for the Korean sites, they also use aluminum alloy. Oops, sorry, I meant postmac. And this is their installation process. It is for your reference. You can compare it with the others that we've mentioned. Now its feature is that you can actually adjust the angles of the tilt. If we look in the previous page, you'll see that the angles we see there in France and Japan, usually their angle is 5 to 10 degrees. They are fixed, but the Korean ones, they can actually adjust their angles to maybe around 20 or 30 degrees. Like in this picture, the joint is actually adjustable. Now here is the anchoring method. It is the core technique for sites on the water. This site actually uses concrete blocks under the water to anchor the platform. Below you can see they also use anchors on the bank to help stabilize the platform, and they also have cables underwater. So this is their way for anchoring the platform. This is the Chinese site. It is for your reference. Actually, the installation process of these sites are pretty similar. Now, our first system on the water is this site in a pond in Taoyuan. And it has been a few years, 4 or 5 years. Yeah, so 5 years since its completion. So it has been operating for 5 years. This is also for your reference. Here are some information on this system, basically the concepts of designing the system in this pond. For example, our wind resistance capability can withstand winds up to 58 meters per second, and we also monitor the water quality and ecology in the pond. So the reason is because we want to show that solar power systems won't affect the ecology of the pond. This page shows the construction process. It is also for your reference. The core technique also includes the float and the supporting frames. We've mentioned previously that different vendors from different countries use different materials for their floats and support racks. Actually, the most important thing is the anchoring system. And of course, how you anchor the platform would depend on the length of the anchoring cables and also the geology of the surrounding areas. Yeah, so as you can see here in this picture on the top, they basically anchored the anchor into the ground on the bank to secure the platform. And also there is the concrete blocks and other different ways for installation. This is a holistic SWOT analysis on the sites on the water. It is also for your reference. And this is the site that is currently still being constructed. It is located in Miaoli Holong's flood detention basin, and it is estimated that we will connect it to the grid by the end of this year. This is the end for this class. Thank you very much.